um, share my screen. Okay. Can you able see my screen? Hello.
Yes, ma'am, we can.
Okay. All right. Thanks for the response. So today we're also going to be doing some talking, and then if there's a little more time, we can just do some practical to just show the simple things we've learned. And so what we're going to do today is data cleaning and pre-processing. Blah blah blah. Data cleaning and pre-processing. Okay, so that's what we're going to be doing today. All right. So data cleaning and pre-processing. So, oh God, why is this word so difficult all of a sudden? Okay. So we did a lot of talking last week on big data analytics methods and how you can use big data analytics, the processes to, I mean, on Monday, the processes to follow, what to do, how to go about it, not just jumping into your data analytics process and all. Please, a minute, please. I'm so sorry. Give me a few minutes. I'll be back. Please, please just give me a few minutes. Please, I need to attend to something. Hello, I'm so sorry. Please, apologies. I really apologize. Deeply apologize. So I'm back. Please confirm that you can hear me. So I'll just move on, please, and that you can still see my screen.
Ma,
Yes, ma'am.
Okay, okay. All right. Thank you very much. So data cleaning and preprocessing. Okay. Um, like you all know, data analysts use data from different sources, right? So before you go into your analytics process, it's very important that you have to evaluate quality of your data. So you cannot just take data from different places and say, hey, I'm a data analyst and then I just want to analyze data. So I'm just going to gather all of this data together and analyze it. No, your data has to undergo pre-processing, and then you have to be sure that your data is of good quality, because you can have a lot of data and then it's of bad quality, say some missing values or some columns are merged together in a funny way and stuff like that. So you have to be very sure that your data is in a good state and of good quality before you and understand the characteristics of your data before you start using your data to create visualizations or before you start analyzing your data. So all of these things that I just said, the process of checking your data, making sure that your data is in a good state and all, it's called data preprocessing. So why do you need to process data? Okay, much of the raw data contained in databases is unpreprocessed, incomplete, and noisy. So databases are like dump places for data. So a customer fills in name, amount of goods bought, value of goods, volume of goods, address, phone number, email address, what again, his department or something, or the kind of clothes he bought, and all into a table, or into a say form or something. And then as it's filled in, it just dumps into the database like that. So it just goes into the database like that. So database just is like the house of the data. It just collects the data that was filled in, no filtering, nothing, just as the customer fills it. So say for example, the customer, instead of filling first name, last name, and gender, he skips last name and fills gender into last name spots, into the spot for last name. So that kind of thing now would cause an error in your data, definitely. And then it just dumps into the database like that. So most of your raw data in databases, or most of the raw data in databases, are not processed, and they are sometimes incomplete too. So in order for data to be useful, or for you to have good data analytics, your data has to undergo pre-processing, and this is called data cleaning and data transformation. So the objective of all of this is to minimize garbage in, garbage out. Like, you know, the meaning of garbage in, garbage out. You are putting in garbage and then you are returning, you are bringing out garbage as output. So you don't want this to happen for your data analytics process. So to minimize garbage in, you process your data, and then this also minimizes garbage out. Of course, data cannot be 100% perfect, but there's a level of confidence that you have with your data to be able to say, oh, I'm very sure that my data quality is 90 something point something percentage. So data cannot be completely accurate, but then data has to reach a good level of accuracy, which shows that you have a high data quality. So those are the reasons you need to pre-process your data. So pre-processing your data is very important. So okay, so why do you need to pre-process your data? Like I said, I already said, missing values. Sometimes you have outliers. Okay, sometimes you want to create some data science models or data mining models, and then if you have outliers, these models will not be properly organized or properly created. So that is why you need to. Okay, I thought someone was coming in. That's why you need to pre-process your data. So that's about pre-processing data, and then data cleaning. So for example, see this data set, or this table, probably from a customer database. um you can see that here you have zip code, you have numbers. Now this is a virtual variable. You don't have, this is not just numbers. Okay, this contains numbers and letters. Now this is numbers. So first of all, you see that this looks odd, right? So this is an example of a faulty value in your data set. This is also 4 characters instead of 5 characters. But it's possible that this is not wrong. It's possible that, say, maybe the zip code for that country starts with 0. And sometimes when you are imputing sometimes phone number into Excel sheet, it takes out the 0 at the back. So this could probably have a 0 at the back. So all of these check-ins are not for you to just take out the data that is wrong and throw them away. It is for you to analyze the reason for having that kind of data in your data table. This one, so there is nothing here. So probably the customer didn't want us to know his gender. So you don't just take out this customer. You try to check the reason for having this particular sorry, I'm trying to admit people. You have to check the reason for having this particular empty space. Probably contact the database administrator or make inquiries or something. Income, yes, there are people that are low income earners, but having a minus in income is obviously weird. So that is to be checked. And so on. So for example, age, you don't have anything like C as age, and then 0 as age. Does it mean the child is a baby? And will a baby be earning 50,000? Oh, okay, that could be possible. Say maybe if the baby was an influencer or something. So all of these things need to be investigated properly, because you don't want to have missing values and wrong values in your data. So that is about data cleaning, investigating wrong values and all. So handling missing data. So a common way people handle missing data is they omit the records of field that have missing values. For example, you now say, because this one has a missing value, I am taking out 1003, which could be bad, because this person might actually be very important to be checked on in your data set. And then you're taking out all of the ones with empty values. So what about the other data fields? What about the zip codes and these? This could actually be useful. So taking out this whole row because you have an empty value here doesn't make much of sense anymore. So you cannot do that to your data now. So missing data is a problem, okay, but you have to think carefully about how to handle the issue of missing data. And then that common method is something that should not still be used now, because you could actually have other valuable information from the other fields in that particular row, for that particular row of data. So you don't just take out rows with missing values. It could be wrong. So therefore, data analysts have turned to methods that will replace the missing value with a value substituted according to various criteria. So now data analysts have ways of replacing these missing values with a substituted value. So instead of just taking out the missing row, they already have ways to put in a replacement for that particular cell or that particular missing value. So let's look at these various criteria for handling missing data. So some of the common criteria for choosing replacement values for missing data are as follows. So one, you can replace the missing value with some constant specified by the analyst. So the analyst could say, if in the gender column there is any empty space, I would put missing, missing. So whenever you see missing, you understand that that person did not impute his gender. Or you could put unidentified or something. So you could replace it with some constant. Another thing people do for numeric value, for numeric fields, that is fields that contain numeric values, is they put 0. So for example, you want to find like the sum, and then that place is you have a null value in a numeric field, you can put 0. So finding the sum wouldn't be would still be correct. But then when you put 0 and then you're finding the mean, then you could have issues with doing that. So depending on your kind of data and depending on the kind of analysis you want to perform, you can determine what constants you can use to replace the missing values. So another thing you can do is you can replace the missing value with the field mean. So you have a column that has numeric values. So say this transaction amount, and then probably this particular place is empty, and then you want to put something here because you want to perform analysis on this column. You want to do like maybe mean, median, or stuff like that. You want to replace this empty place with a value. one thing you can do is find the mean of the whole column, omit the null part, find the mean of the whole column, and then whatever your mean is, you put it here, you put it into your missing cell. So that's another thing you can do for missing data. Another thing you can do for category, and it's usually majorly used for numeric variables. That's for using the mean. You use the mean when you're dealing with numeric variables. For categorical variables, you use the mode. So if you had say name of countries, Europe. Okay, so I'm using a 5-row data set now. If I have 5 rows in a data set, so I have row 1 Europe, row 2 Europe, row 3 US, row 4 Europe, and row 5 US. It means I have 3 Europes and 2 US, right? So if I have a row 6 that has an empty value, I would take the mode of the column. The mode of the column will be Europe because I have 3 Europes, right, which is the highest frequency. US has just 2. So I'll take the highest one, which is Europe, and then put Europe into row 6 that has the missing value. So that's another thing analysts do sometimes for categorical variables. Another thing you can do is replace the missing values with a value generated at random from the observed distribution of the variable. So you just look at the column and then you just generate any value at random from the observed distribution. So you observe the distribution and then you just replace it with anything that you feel is most suited for the missing value at that particular point in time. That's another thing you can do. And all of these first 3 methods are not very accurate, usually very accurate or reliable. So most of the time, these first 3 are not very reliable. Okay, so the best or most reliable method is 4, and 4 is replacing the missing values with imputed values based on the characteristics of the record. So may say you come here and then you look at this person is a male, and then is married, he has this income, and then he lives in this particular area. So if somebody that has income around 75,000 and is a male, and then lives in this particular area, if there's anybody like that, I would probably say is a male based on his other characteristics. So that's another thing you can do. And then this method, you don't just do it as I've said it. You do it with some analytics methods, okay? And these analytics methods are advanced analytical techniques that we've not discussed yet. So it's called, this is what I just discussed now, is called imputation, okay? It's called data imputation. You are imputing missing values based on the characteristics of the record. You know, a row is called a record. A row is called a record. Let's note that. So you are imputing missing values based on the characteristics of the record. So that is called imputation of missing values. And then it is majorly used in advanced analytical techniques. So we've not discussed this advanced analytical techniques, but then we'll be discussing it later on, but not today. Not today. So that is that about the 4 methods that are majorly used for replacing data or handling missing data. So identifying misclassifications. Okay, so for example, there's another thing that can happen with missing values or with wrong data input or wrong data entry. Now see something, this is US, this is France, this is US, this is USA, this is France, this is US, this is Europe, and this is Japan. So you see that USA is 1 and US is 156. That should raise some suspicions that USA, you cannot have just frequency of one country. So there is probably another US somewhere, maybe that doesn't have an A or that was wrongly spelled, that contains all of the other values. And then you can also see that, you can see here that US has 156 and USA has 1. So you have to merge these 2 records together. So that's another thing with misclassifications. You could also identify misclassifications. So that's that about checking for missing data. So now we'll move on to graphical methods for identifying outliers. So outliers are extreme values that go against the trend of the remaining data. And I've explained outliers when we're doing box plots, when we're doing drawing graphs, when we're plotting graphs in R, I explained outliers. I explained how you can identify outliers. The 1.5, the Q1 of interquartile range, or Q1 minus 1.5 of interquartile range, comma Q3 plus 1.5 of interquartile range. So if your data point doesn't fall within this range, then it is an outlier. I remember I explained that, and I showed us a video. So even if it's a video you can recollect, I remember I did that. So I don't want to go too much into how you can recognize outliers. So those are outliers, and then they are usually represented. You can see them in box plots. Sometimes you can see them in histograms and in scatter plots too. So outliers is important. Outliers are important. Identifying outliers is important because they may represent errors in data entry. So they may. So it is not all the time that outliers are errors. Sometimes your outliers actually point you to some very important characteristics of your data. So you don't just identify outliers and take them out immediately. You identify outliers, investigate them, and either say they probably still remain an outlier, or they are not an outlier. So that's what you do with outliers. You don't just take outliers and then throw them into the dustbin. No, you have to investigate the reason for having those outliers and then see if they're actually really outliers, or they are very important things you need to check in your data set. So certain statistical methods are sensitive to the presence of outliers and may deliver unreliable results. So there are some statistical methods that you might want to make use of, and then these methods are sensitive to the presence of outliers. So in those particular kind of situations, you might have to find something to do with the outliers, normalize your data, which we'll be discussing, and so on and so forth. So that is about outliers. So one graphical method for identifying outliers for numeric variables is to examine a histogram of the variable. So you can examine a histogram, and then examining the histogram will help you identify outliers and show you where your outliers fall. So that's about graphical methods of identifying outliers. So measures of center and speed. I'm sure we, at one point or the other, we've come across measures of center and speed. If you can finish on time today, it's very nice. We're always finishing very late. So measures of center and speed. Okay, before I move on, any questions? I've been talking since, so let me see. Any questions? If there are no questions, just tell me to go ahead and that you understand what I've been saying so far.
No question, ma'am. You can continue. Thank you.
Okay. All right, cool. So I'll just continue. So measures of center and speed. I'm sure at one point or the other, we've thought about, or we've come across measures of center, probably in secondary school or so, right? So measures of center and speed. You probably have heard of mean, median, mode, and all of that. These are measures of center. Okay, so measures of center, mean, median, mode, and so on. They are measures of center. So suppose we are interested in estimating where the center of a particular variable lies as measured by one of the numerical measures of center, the most common of which are mean, median, and mode. So measures of center are a special case of measures of location. And the measures of location are quartiles, okay? Quartiles, percentiles, those are measures of location. So you are measuring the location of your data, percentiles and quartiles. And I remember I explained quartiles to us. Percentiles is like percentage. It falls in the first 10%, second 20%, third 30%, and so on. So those are measures of location. So measures of center are a special case of measures of location. Okay, and then the mean of a variable is simply the average of the values of the valid values taken by the variable. Valid values mean not null values, valid values. So you are taking the mean of a variable. It means that you are taking the average of the valid values taken by the variable. Measures of location are not sufficient to summarize the variable effectively. So sometimes you might have same values for mean, median, and mode of a distribution. and this distribution actually has different natures. So sometimes method of center and speed are not sufficient for you to summarize a variable effectively, because you could actually have same mean, median, and mode for a data set, and for two different variables, and these two different variables have different natures. So sometimes they're actually not sufficient for checking, for measuring your data, or checking your data, or looking at what your data looks like, or checking the characteristics of your data, and so on. So an example of that is if you have, let me see, I'm trying to see where I can. Okay, I think I shared just one screen. Let me share my whole screen, or my whole system. Okay, please confirm that you can see my screen.
Yes, ma'am.
Okay. Okay. So trying to see where I can quickly show something. Okay. Or instead of this, let me okay. Instead of this, let me just go to our R studio and then just show us there. So HD user. Okay, it's taking so long. Okay, so I don't know why this is taking so long. So I just wanted to show us that you could have two data sets that are different, and their means, median, and modes are the same thing. So that's what I want to show us. I don't like when my screen does this. I don't know why it's doing this. Okay. Okay, so let's move on. Let me just move on. It's taking too much time. So I would show us that we could have two data sets, and then their mean, median, and modes are different, which means that I cannot easily determine the characteristics of my data from mean, median, and mode, because they have the same mean, median, and blah blah blah. Because they have the same mean, median, and mode, so I might not be able to easily determine the other characteristics of my data based on the mean, median, and mode. Okay, so that is one thing about measures of location. They are useful sometimes, but then sometimes they don't give you exactly what you want. So sometimes you still have to transform your data. So which moves us into data transformation. Okay, so data transformation, variables tend to have ranges that vary greatly from each other. Therefore, data analysts should normalize their numeric variables in order to standardize the scale of effect each variable has on the results. So sometimes you have a data that sometimes you have ranges of your variables that vary greatly from one another. So for example, now they gave an example in your textbook. They said in a baseball game, okay, players battling averages. I think that is one of the aspects of baseball games. So players battling averages will range from 0 to less than 0.4. And that's one variable, right, for the game, for the gaming or something, or the baseball gaming. Then another variable is number of home runs. So players battling averages ranges from 0 to 0.4. Number of home runs will probably vary from or range from 0 to 70. Now see the range. The range is huge. So you cannot just use these two variables and expect to have accurate results. So there are some things you have to do to these data to normalize the data so that they don't have ranges that vary greatly from one another. So there are several techniques for normalizing your data. Okay, and then we have the here we're going to talk about the mean max normalization and the z-score standardization. So those are the two techniques that we're going to be talking about here. So the mean max normalization works by seeing how much greater the field value is than the minimum value of x and scales the difference by the average. So all of these formulas are in your textbook. They are not indicated here, but all of these formulas are in your textbook, and then you can check them, check on them or something. Then the z-score standardization is very widespread in the world of statistical analysis. It works by taking the difference between the field value and the field mean value and scaling this difference by the standard deviation of the field values. So let me put this in formula. So min-max normalization is, if you have your textbook, you can follow along. The formula is there. Let me see, where's my textbook? So I'll just show you, tell you the page. So if you want to check the formula as I'm saying it. So okay. Okay, so I skipped something here. Okay, so it's not here, but then let me just talk about it. So measures of center, which is a special case of measures of location. Okay, like I said, it doesn't totally give you the full characteristics of your data. So sometimes you might actually have to check the measure of spread or the measure of variability. That is, how widely spread is your data. A data set will range from 0 to 4. Another will range from 0 to 70. So there are some measures that you can put in place to check how widely spread your data is. And these are measures of spread. Okay, so measures of spread are things like, not speed, it's spread, I think. So measures of spread are measures that include range. And we all know what range is. What is range? Range is maximum minus minimum value. So the maximum value minus minimum value is your range. Then we also have standard deviation. Standard deviation is, if you remember standard deviation from school, you subtract the mean from all the values, right? Square it over n minus 1. I'm on page 433 of your textbook. The formulas are there. I cannot, I won't be able to like put down the formulas. Assuming there was a board, I could just easily write out the formulas, but there's no board. So you can follow on page 433 of your textbook. It's good to know that we have a textbook. So square root of the summation of all the deviations from the mean, square it over n minus 1. So n is your number of variables. Number of variables that you have. I mean number of values in your variable. So that is n, or number of observations. Let me put it like that. Let me not confuse us. N is number of observations. So that is standard deviation. We also have the mean absolute deviation, which is the deviation from the mean, deviation of all the values from the mean. We also have the interquartile range. Interquartile range is Q3 minus Q1, which is quartile 3 minus quartile 1. We also have the, which one again do we have? Okay, that's all. So all of these are the measures of spread or measures of variability. So these are the other things you can use to check for other characteristics of your data aside the measures of center, which is mean, median, and mode. So when mean, median, and mode fails, you can go on to use the measures of spread to check the spread of your data. Okay, so data transformation. Give me a minute, please. Okay, I'm back. All right, so data transformation, min-max normalization. Min-max normalization is, like they said, you are checking how much greater the field value is than the minimum value. So minimum of the whole column, right? So say your minimum value in the whole column, maybe you have values 1, 2, 3, 4, and 6. The minimum value is 1. So you take out the minimum value from each of the values, and then you divide by the range of x. And what is the range of x? Maximum minus minimum. So that is min-max normalization. Okay, so normalization is like this. Your let's say you have values let's say you have values 1, 2, 3, 3, 4, 5. Okay, and then you want to find the min-max normalization. So it will be each of these x values. Okay, so each of these x values minus the minimum value of x. The minimum value of x, right? And the minimum value of x here is 2. So each of these values, so 2 minus the minimum value of x, which is 2, then everything divided by, I'm just using this to show the formula, everything divided by the range of x. So this is what normalization, min-max normalization is. So this is the formula. So it does this for all of the values and then gives a value based on this. Okay, so let's see if we can quickly do this. So we have x min max, let's call it that, and then let's do x minus minimum value of x divided by range of x. Okay, so let's do it like this. So the range of x will be, so r will be what? R is the range of x, and to be maximum of x minus minimum of x, right? Okay, so let's see how this works. So let's see what r is. Okay, so maximum of x minus minimum of x, that's 5 minus 2, which is 3, right? So I want to find the normalization values. That'll be all these x values minus the minimum of x divided by the range. So let's see. So let's check what's x normalized. So this is it. So these are the normalized values. And you can see the normalized values are between 0 and 1. So the spread of the values have reduced, right? So we don't have so much of spread anymore. Like when we had 2 to 5, which was like 3. We had 3. The spread was about 3. Like the distance between the highest and lowest value was really huge. But now see that the spread is actually really reduced. We don't have so much of so much of spread anymore, and this will still be a good representation of this data that we already have before. So this is one method of normalization. Okay, and then this is the min max normalization. So another type of normalization we have is the, so most of the time your min max normalization ranges between 0 and 1. Okay, so it ranges between 0 and 1. And then this is because, for example, you want to find, okay, for example, if you look at this, your highest value will give you 1, your lowest value will give you 0. And if you add a value in the midpoint, okay, say maybe you had, how will I put it now? Not really a value in the midpoint, but maybe you had a value that was in the mid range of 2 and 5, your x normalized value will be 0.5. So let's see something. If we had 5 plus 2 is 7, right? 7 divided by 2 is 3.5. So let me change this to 3.5. Okay. Let me change this to 3.5. Then do this. Then do this. Then do this. So you see 0.5. Now, why did I change this to 3.5? I wanted to show you that when you have a value in the middle, like you have a mid-range value. So a mid-range value is a value that the maximum of x plus the minimum of x divided by 2 equals to 8. So what is the maximum of x? 5. The minimum of x is 2. Okay, so if you divide 5 plus 2, 5 plus 2 is 7, right? Divided by 2, that is 3.5. So 3.5 is a mid-range value because it is in between the maximum and minimum value of your data. So of your data set. So or of your field values. So 5 plus 2 is 7, divided by 2 is 3.5. So if you find the normalization of any mid-range value of a data set, your normalization value will always give you 0.5. Then your maximum value will always give you 1 as the minimum maximum normalization value, and then your minimum value will always give you 0. So most of the time, your normalization values for min-max normalization is always between, it's not most of the time, all of the time, it should be between 0 and 1. If the minimum value will give 0 and maximum value will give 1, then you have all of the data points within, so they should be between 0 and 1 for the normalization value. Any questions on this one before I continue? Okay, I'll take that as no question. So that means we understand. Okay, thank you. All right, so no questions. So that's about min max normalization. So we also have the z-score normalization. Okay, z-score normalization to normalize your values. Note that you would use these values. These are the values you would now use to plot your graph. It will still represent your data values, but then it gives a better spread of your data values and help you, say you started building models, it helps you build better models. And there are some models that cannot work with huge spread. So this is just a small example. There are sometimes you have huge data sets that you have to perform normalizations on. So it's very, very useful in real world scenarios or situations. So for z-score normalization, z-score normalization is like this. So you have the formula is like this. So your z-score is, oh my god, is my system low? Okay, it's not low. Okay, so okay, let me just continue. All right, so z-score normalization is x value minus the mean of x, okay, and all divided by, everything divided by standard deviation of x. Okay, so sorry, I want to quickly check something. Quickly check something. Let's quickly show something. Okay. Okay. Okay, that's fine. Don't worry. I would show us later. So let's do, okay, so let's quickly check the z-score for this one. So want to check the z-score for this. So this would be we have this as x values. So let's say z-score will be x minus mean of x divided by standard deviation of x. Okay, so z-score. So this is z-score. So z-score This is the z-score, okay? So this is another way to normalize your data. And then z-score, okay, so it's as if z-score doesn't have any particular range, right? Okay, z-score doesn't have any particular range, okay? But when your value lies below the mean, you have a negative z-score. And when your value lies above the mean, you have a positive z-score. So for 2, we had a negative z-score. This is because 2 lies below the mean. So what is the mean of x? Let's see the mean of x. Mean of x is 3.5. Oh, okay, which is the mid-range. Okay, same thing. All right, so the mean of x is 3.5. So 2 is below the mean, and that's why we have a negative z-score. And 4 is above the mean, so we have a positive z-score, and so on. So when your value lies below the mean, you have a negative z-score, and then above you have a positive z-score. So you can use any of these two normalizations. You can use, maybe in your data set, you could try to do any of these two normalizations. Anyone that gives you a better representation of your data is what you go with. So these are the two examples of normalizations. But in normalizing your data, if you're normalizing the data for a client or for a particular organization or something, you have to let them know that you performed some normalizations on the data. You don't just go ahead and perform normalizations on the data. Also, in building models, of course, you might have to perform normalization on your data. But then the client has to know the documentation process. So you are cleaning, it's just like cleaning data, and then you are telling the clients that, okay, when I was cleaning your data, I changed all the missing values. I put Europe in all the missing values and stuff like that. So there is documentation on the data. So aside that, normalizing values is a very good thing to do when you have a huge spread in your data. So those are the two types of normalization. So there's also another thing you can do to ensure that all your normalization values lie between -1 and 1. Okay, so let me see if it's on my slide. Okay, it's not. Okay, so let me open the next slide. 1057. Okay, this is numerical methods for identifying outliers. So we are not yet here. I'm still trying to explain some other things. Okay, so let's come back here. All right, so decimal scaling, there's something called decimal scaling. Decimal scaling. All right, so decimal scaling ensures that every normalized value lies between -1 and 1. So how do you do decimal scaling? The decimal scaling is, so let's say x decimal, let's call it x decimal. The formula is the formula for decimal scaling is x divided by 10 raised to power d. Okay, so this is the formula for decimal scaling. And then d, where d is the number of digits of the most maximum value, or the maximum value in your data set. I know that's a lot of English, so let me come again. So if I had a data set like this, so let me use another data set. Let me have y to be 4, 5, 6. Okay, 4, 5, 6, 4, 3, 1, 20, 2, let me see, 200, 140, 312. So we have this as y value. So I want to find the decimal scaling for this y variable or y object. So I'm going to do, let me call it y decimal, equal to y divided by 10 raised to power. So now what is D? Okay, so you look for the maximum value in your data set. So the maximum value of Y, these are just representations. This is not this cannot be applicable in real life scenario, because of course this is very, very small compared to huge data sets that you're working with. But then I'm just trying to practicalize what we've learned with samples. So maximum value of Y is 456, right? So you would take the absolute value of the maximum value of Y. So what's the absolute value? We already know the absolute value. Absolute value of Y, of maximum value of Y. It's still going to be the same thing, right? So the absolute value of maximum value of Y is 456. So you count 456. You count 4, 5, 6. That is, how many digits does it have? So D is number of digits. 1, 2, 3. So it has 3 digits. So it will be Y raised to power 3. 3 digits. Okay. So that is decimal scaling. And then let's check what Y decimal is. So this is Y decimal. Okay. So it ensures that every normalized value lies between -1 and 1. And then you can see that your values, they lie between -1 and 1. So it just helps you to check your data and ensure that they actually lie between -1 and 1. So that's what decimal scaling does for you. So since they lie between -1 and 1, then of course your normalized values are okay. You're good to go. So this is what decimal scaling does. And then okay, I've explained the formula already. Okay. So yeah, that's about decimal scaling. So very quickly we'll just go to, there was something on this slide. Let me see. Okay, still numerical methods for identifying outliers.
Now I have it.
Okay, yes. Go ahead.
Let's scale between my future scale.
Is what? I can't hear you.
It's decimal scaling. Future scaling.
Something is making sounds. I don't know. Behind you.
Can you hear me?
Okay, I can hear you, but are you close to a microphone or something? Or radio or something? Okay, just tell me. Is decimal
Scaling and future scaling the same?
and future scaling?
Yeah, future scaling.
Future scaling. I don't know. I don't know if it's another name for it or it's the same. I don't know. I'm not sure about that. But I think feature scaling, I think I've heard of feature scaling, right? It is a data normalization technique, but I don't know if it's the same process that you'd use with this type of scaling, that is this decimal scaling. So I'm not sure if it's the same thing, and or if you know about it, you can tell us. But then feature scaling is a data normalization technique, yes, but I don't know if it's the same thing as decimal scaling. I'm not sure if it's the same thing as decimal scaling. So what do you understand with feature scaling, since you even know about it?
They kind of do the same thing. That's why I'm asking.
Okay, because they kind of do the same thing.
Yeah,
Okay.
from -1 to 1.
From -1 to 1, okay. It's probably the same thing. I don't know. I know it's a data normalization technique, and it might be similar to decimal, or it might be the same. I'm not sure, but I cannot say if it's exactly the same thing. So you can help us check that and tell us. But then I know feature scaling is a normalization technique. I know that. It's also a normalization technique. There are so many normalization techniques. This textbook might not have everything, but I'm sure it has the important ones that we need to know. So we can check if it's the same thing or it's another type of scaling. So so that is about decimal scaling. So transformations to achieve normality. You might have to do this on your own. Is in your textbook, page 435. Transformations to achieve normality, and so on. But then, okay, so the problem is we need a data set to show this, and we don't have the data set that we're given. So they're just showing us the transformations you can do to achieve normality. And then there's also a way you can check for skewness of your data. You can check if your data is skewed to the left or skewed to the right. Now, I think we all know what a standard normal distribution is. A standard normal distribution has a normal curve. Okay, so you have your mean in the middle. Your mean is 0, and your standard deviation is 1. So your deviation from the mean, your standard deviation is 1, which is deviation from the mean divided by n minus 1. Deviation from the mean square divided by n minus 1 square root. So that is your standard deviation. So a curve where you have the mean to be 0 and the standard deviation to be 1 is a normal distribution. Okay, so sometimes your distribution is skewed to the left or to the right. So let me quickly show something. It's not here, but okay, so let's quickly do this. Standard normal, okay, standard normal distribution. Okay, so you can see a standard normal distribution. A standard normal distribution has its mean to be 0 and then standard deviation to be 1. So this is what a standard normal distribution looks like. Equal number of points at this side, equal number of points at this side. This is what the standard normal distribution looks like. So let's check a skewed distribution. Skewed. Okay, so for example, you say this is skewed to the left because you see that you have more points generated towards the left of your curve. And then if it was the other way, okay, so this is it. There is no skewness in this one, right? This doesn't have any skewness. This one doesn't have any skewness. This is skewed to the left, called positive skewness. So you have more values at this side, and this is skewed to the right, negative skewness. So that is what you call skewness of your data. And then skewness of your data can be measured. Okay, you can measure skewness of your data. So this is where you measure skewness of your data. Somebody's trying to come in. Okay. So this is where you measure skewness of your data. So skewness is 3 mean minus median, all divided by standard deviation. So this is the way to measure skewness of your data. So I could measure the skewness of this data. Let me measure the skewness of this data. So skewness equal to 3 multiplied by mean of y minus median of y. Okay, then everything divided by standard deviation of y. Attempt to apply non-function. Okay. Attempt to apply non-function. I don't want to do it separately. I want to do everything at once. Let me see. Okay, let me see if it even did anything. Okay, so So let's see what this one gives us. Okay, this actually works. Median of y. Okay. Okay. So what's the problem? Let me try to do this. Okay. So let me do one after the other. So let me call this D. Mean of y minus median of y. Okay. So 3 multiplied by D okay, so that works. Attempt to apply non-function. I'm trying to understand what that error is, but then let me not just waste time. So this is skewness, okay? So this is a negative skewness, and then I was showing us something here. Negative skewness, right skewed. Positive skewness, left skewed. So when you have negative skewness, it means your data is right skewed. So here we have negative skewness. So it means our data is right skewed. So let's see our data. 456, 431, 200. So let me do something. Okay. So look at this thing. We have, I actually just want the points to show. Okay. Okay. Whichever way. So let me just explain from here. We have 456, 431, 200, 312, 140. Now, we have more of large data points. If you look at this, you have more data points towards this side. Okay, you have 300, 400, 500, and so on towards this side. Something I can do again to show it better is, let me see if I can use, let me use breaks. 4 to 5. Let me see if to break this down. Okay, still breaking down. Okay, so this is because we don't have so much frequency. Okay, so we don't have a lot of data points. That's why we are having this. Let me try to add more data points. I want to explain it properly. So I want to add more data points. 300. Let me add more data points towards this side. Okay, so let me check the skewness again. So let me do the skewness again. So skewness, let's check the skewness. So the skewness is positive. So let's come here. So what is positive skewness? We have the data skewed to the left. Okay, so if you look at this, you see that the data is majorly skewed to the right. I'm not sure if this is telling me the right thing. Left modal. So we have the frequency at the left side. That's what gives us positive skewness. So the highest frequency, the one with the highest frequency is at the right side. So maybe their left is different from our right. But then basically what I want to explain is the data is skewed to the right. Okay. So if you were to draw a line on this, you see that the data is skewed to the right. Let me see if I can draw a line on this. Let me draw a line on this. I want to draw a line on this. So let me do. Okay. I can do LTY, right? me see if this would draw a line for me. Okay, so you didn't. So I'm trying to draw a line on this. Someone should remind me. I'm trying to draw a line on this. A line on the histogram. So let me do it in. Nobody can remind me how to draw. You people, you're always waiting for me. Okay, it's fine. I don't know why this is not working. This should work for me. So let me try to do something else. No. What are different line types we have? Oh, you can remind me the different line types we have. I think I'm right? Solid. Solid. Okay.
One, I think.
What did you say? Solid is 1. Okay, so we should try using just 1. Let's see if 1 will work.
Yes.
Okay, not possible. Okay. Oh wow, my battery is low. Give me a minute. Let me quickly plug in my laptop. Okay, so let's not dwell too much on that. Okay, let's not dwell too much on that. Let me just okay. So my explanation is just that when your data is skewed towards the right, you should have positive, and when it's skewed towards the left, you should have negative. Sometimes these online things can be very confusing. So we have more of 312, 317, more of data sets, data points above 200 in our data set, in our variable y. So that's why you see that it's skewed to the right. And then when it's skewed to the right, you have a positive skewness. When it's skewed to the left, you have a negative skewness. So that online thing is really confusing. If I were to check for something else now, say let me use this, and maybe if we had, can you mute yourself? Okay, thank you. So maybe if we had, let me do 12, 13, 15, 24, 25, 35, 37, 39, 36, 35 again, 34 again. So let me show this, okay? And then I want to construct a histogram for this. I don't know why my line is not showing. I want to construct a histogram for this. Oh, okay. It's still widely spread. I still need to add more. Okay. So oh, I'm still putting it towards this side. Okay. We now have Okay, so if you look at this, we have more of data points where towards this side, right? Let me add more. Let's say we add more data points towards this area. Okay, so we have more of data points toward this area. Now let me check for the skewness. So let's see what the skewness will give us. D. So D is, let's say D1. Then we have mean of, is it S? Yeah, S minus median of S. Okay, then skewness will be 3 multiplied by D1 times standard deviation of S. So let's see skewness. Oh, we still have 0.949, but let me see the first one. What was the first one? So the first one was 0.2, which was moving towards the moving a lot towards the negative axis, right? But this one is 0.9, is farther away from the negative axis. So the when you have skewness to the right, when you have skewness to the right, that means you have more higher values. So your graph usually tends towards the negative axis. So that's why, I think that is why we have it here, that this is negative skewness. So it tends towards negative axis. So we don't have enough data points to be able to represent a huge skewness to the right. Let me bring that person in. So we don't have enough data points to be able to represent skewness to the right. That is why we have 0.2 something. So it is tending to the negative axis. Okay, but this one you can see we have positive skewness, so it's going away from the negative axis. So that is about skewness. If we had more data points, we would have been able to show it properly, but then our data points are not sufficient to show it. So the skewness, we don't have enough skewness to show that it is very much, we don't have enough data points to show that it is very much skewed towards the right. So if we had more data points, it would be able to show more skewness towards the right. So that's about skewness, and this is the formula for checking for skewness. So you can try it out with data points, with normal data values and all, and then you would be able to see the right skewness and left skewness better for data points. Okay, so let's quickly move on from this and go into numerical methods for identifying outliers. So let me come back here. Numerical methods for identifying outliers. Okay, so numerical methods for identifying outliers. So the z-score method for identifying outliers states that a data value is an outlier if it has a z-score that is either less than -3 or greater than 3. So when a data point, when you calculate the z-score for a data point and it gives you a value that is less than -3 or greater than 3, then that value is an outlier. So you can use the z-score to identify outliers. Then variable values with z-score much beyond this range may be there for the investigation. In order to verify, okay, so However, one should not automatically omit outliers from analysis. So, sorry, back to this. We don't have a good data to be able to show this skewness and all. But then, maybe if I'm able to get hold of a good data set, I'll be able to show us better right skewness and left skewness, and also plot the lines to be able to show us these examples of skewness. So this data is not sufficient to show the skewness I want to show us. But then, when most of your data points tilt towards the right, it's right skewness, and when most of them tilt towards the left, it's left skewness. So that's about skewness. So with a better data set, we'll be able to show this, and then plotting the lines too. The lines too would be able to show us this. So show us the skewness. So we can do this again, but then with a better data set. So, but you understand the concept behind skewness and how to find it. That's the major thing. So variables with Z scores much beyond this okay, bear further investigation. I've said that. So one should not automatically omit outliers from analysis. Like I've said, do not automatically omit outliers from analysis. You have to investigate why you have these outliers in the first place. So flag variables. So there are some analytical methods that you use, and then sometimes you can also use flag variables. And then flag variables, they are like associating values with either zeros or ones. So, for example, if you have a categorical variable that takes only two values, maybe sex, and sex is male and female, okay, you can say if sex is male, then your sex flag should be 0. Otherwise, it should be 1. So anytime you see sex flag to be 1, you know that it is male. Anytime you see sex flag to be 0, you know that it is female. So this is used sometimes instead of the normal male and female variables. And then sometimes it's also used in some modeling techniques, like regression analysis and all. So sometimes you use flag variables, you use variables to represent your data instead of using the data itself. So that's what flag variables is about. So okay, I already talked about this one. This is it. If sex equals to female, then sex flag equals to 0. If sex equals to male, then sex flag equals to 1. So wherever you have 1, you know that it is male, and wherever you have 0, you know that it is female. So that is about flag variables. Flag variables can be used for other things too, but then it is majorly used for two categorical when you have your categorical variable only takes in 2 values. That is when it is majorly used, but it can also be used in other situations too. That's not about flag variables. So removing variables that are not useful. Some analytical methods such as regression require predictors to be numeric. The data analyst may wish to remove variables that will not help the analysis, regardless of the proposed data mining task. Okay, so sometimes in modeling and all, in creating models, you might want to use only numeric values. You might not need other values like maybe sex and all. And then that's another reason for using flag variables, because flag variables help you convert your normal varchar variables or your normal strings to numerics. So sometimes you need flag variables for modeling, because sometimes in modeling, for example, in regression modeling, when you start going to regression modeling, you would understand what regression modeling is about. But for example, now in regression modeling, you cannot use string characters. You have to use numerics. So that is one way flag variables can be useful, using zeros and ones and so on. So sometimes you might want to remove variables that will not help the analysis, okay? And there are sometimes you need to convert your variables to flag variables and so on. So sometimes some of these variables that you want to remove, some examples of them are unary variables. Now, unary variables are variables that take on a single value. So for example, you have you are performing analysis in an all-girls school. So and you have a column that has to do with sex. Now there's a sex column. And you're performing analysis in an all-girls school. Okay. the sex column is already a unary variable because the sex column is going to take in only females, right? There's no male in an all girls school. So that kind of variable, the best thing to do with that kind of variable is to take it out because it is not useful for you or for your analysis or for your prediction. There's nothing you're going to use all female, a column that has all female to do. So that kind of column, take it out. Then you could also have some that are nearly unary, and then sometimes you have to know whether you should remove it or not. So, for example, an example that was given in the textbook is when you have a game that most females play, and then you have like maybe 2 males playing the game. So you have like say 15 females and 2 males. Sometimes you have to leave the column because you don't know if there is an insight you need from that column. You might need to use that column for future references to be able to say that, oh, we had this percentage of males that played in this month, and last month we had ×2 of this number of males that played or so. And if you weigh the circumstance and you discover that it is not a variable that will be needed, then you can take it out. So those are close to unary variables, columns with close to unary variables. But then most of the time, unary variables are usually removed. Those columns with unary variables are usually removed. So that's about removing variables that are not useful. So variables that should probably not be removed, okay? Which or more of the values are missing. Sometimes you see your data and you have like 90% or more of the values in your data missing. Then you are like, this column is very, very not useful, and then I just want to take it out because I have like over 90% of my variables missing. Sometimes you should not remove them because sometimes there might be some insights from the remaining 10% data that you have left in that particular variable. So in that particular column. So sometimes you shouldn't remove that. And then variables that are strongly correlated. So sometimes you have let's say number of females and number of say hairs bought. Now guys don't buy hair, men don't buy hair. So these two variables are strongly correlated, meaning that your number of females will probably be equal to the volume of, will probably be strongly correlated with the volume of hair bought. And your number of males will be strongly correlated with the number of shoes or male shoes now, with the number of male shoes bought. So you might want to take out one of these columns and leave one of them. But sometimes you should not take them out because there might actually be usefulness for that particular column. So these are some of the variables they should not remove. And then they're just telling us that the bottom line is that you shouldn't remove variables just because there are a lot of missing values. So sometimes you should keep these variables and see if they can be used before you take them out. Okay, so that's that about that. Let me see if I still have something. Okay, so there are some practicalizations of what we've learned today in your textbook. I really want us to close early today, 11:45 maximum. So there are some practicalizations of what we've learned in your text. Can we close by 11:45? Okay, let's see. There are some practicalizations of what we've learned in your textbook, so you can go through them. But let me quickly see if we can try so excuse me please. Okay, so I'm back. So so let's see what we can quickly just practice before we move on. Okay, we can even see if we can try the skillness with this data. So the data that was used in this textbook, they didn't make it available and they didn't tell us where to get the data in your textbook on page 443. But then we can quickly try something with the empty cars data set. So there's a data set, empty cars, data set. So let's see. So this is the empty cars data set. Okay, and then we can even see if this would if the skillness will work for this one, or the lines that were not working. I don't know why they were not working. If it will work for this one. So I'm in your textbook. Oh, like I'm on your textbook, page 445 to the end. If you want to follow along. Okay. I think the issue I had with this one was it needs to be placed in it. So let me try something with this. With this one I was trying before. So we already have the histogram here. So let me create a, okay, this is S. So let me do this with S. Histogram of S. Okay.
Hello, please, am I still on this call, please? Hello.
Yes, you are. Hello, Sunday.
Thank you, thank you. This one where everybody just silent like this. What's in the happen now? After what I started the assignment, I beg the SQL 20 question assignment. Daniel, are you saying something?
Is Bristol not taking the class again?
I think maybe network logged out or something.
Okay.
Oh, she's back.
Hi, I don't know what happened to my network. Oh, I'm very, very confused. I still don't know because I don't know. My data did not finish. I don't know. So I cannot really explain what happened. So I'm sorry. But then let me just. Time was almost. I was even about calling Manuel to just tell you to go and try it out on your own because I was really trying to sign in. So I'll just not keep everyone waiting. So yep. So let me see. Let me create a box around this. Probably that would help. So plot then LTY equal to solid. Okay.
Share your screen here.
Oh, okay. That's true. Okay, I'll share it now. I'm coming. I'm coming. I'll share it now. Okay. Share. Okay, you should be able to see it now. Let me know when you can see it.
Screen is visible.
What did you say?
Your screen is visible.
Okay. So I created a box around this, but so I don't know if I explained. I taught us this one that time. So this is where you create a box around your plot. Then for the line, I think I got something. So let's see if we can create a line for this. I'm not sure. Um, okay. So it's still not working. Okay. I don't know. I'll figure that out. But in the meantime, let's quickly just um see what we can do with empty cars data set. So empty cars data set. This empty cars data set. Okay. And I want to see. Let's try to. Okay. So let's try to show DISP on a histogram. Sorry, I need to. Okay, so let's try to show DISP on a histogram. So empty cars, DISP. Okay, so this is DISP on a histogram. So let's assume that we had a faulty point. So let's say okay, so let's see the range of this particular data set first. So let's see the range of DISP. Is this the way to get range? Okay, So it's between 71 and 472, right? Then we want to okay. So let's change one of the data points. So let's change one of them to 0 or something, or to 472, right? Let's change one of these DISP data points to 15. So let's do so it will be row 3, column 3. So 3 by 3. We want to change this to 15, one of them to 15. So this 3 by 3. Oh, okay. It's row by column. So 3 by 3. Let's change this to 1500 or something. Incorrect number of subscripts on the matrix. Row, comma, column. Okay. What's it telling me? Or let's okay, maybe let me assign this to a variable first. Let me assign this to a variable. So let me assign no, it should still work now. Okay. So incorrect number of dimensions. Can anybody see any error here? I'm trying to look for the error here. Did I load in empty cars already? I did. DISP.
Isn't DISP
Oh, wait.
variable?
This is where I have the error. This is where I have the error. So, okay. You
I
are not
was
paying attention. So the thing is, okay.
I was
For
about
the
to say
person,
it, but you didn't hear me.
oh, you were saying, okay, thank you. So I'm subsetting DISP on 3, which is very wrong. I'm supposed to just subset empty cars by 3 on 3, or subset it by the column name and the row number or something. So that's where my error was. So what I want to do is 3, position 3, I want to replace this with 15, and that's what I've done. See, it has been replaced with 15. You can see that it has been replaced with 15. So let me now create the histogram again. So you see, so the histogram shows that there's a particular point that is completely out. So this is a way you can use histogram to show outliers. So the histogram will show you that, oh, there's a point that is completely out. So that's about using histograms to find outliers. Then which other thing again in the manual? You already know how to create histograms, so I don't need to like explain all of the X limits, color, border, and so on and so forth. But I explained that you can also create a box too around your histogram. So it takes in this constant argument. That is, you should put the box on the current plot. You want a solid line, and then we want the color to be black. So this puts a box around your plot. Then you could also use scatter plot to see data points that are outside, that are outliers. So plot let's plot empty cars DISP, right? And then okay, do we need to label it? You know, you can label your data if you want. I don't want to go into all of that. You can label the first one as, you can label this as weight. We can leave Y label as frequency. And then we can put a title too. If you want, you can put a title too. I'm sure you all know this. I'm just doing this, not that you do not know it. We've done it before. You could also make the color blue or green, whatever color you want. And then, so this is scatter plot, okay? And then we want to see, so, oh, what did he plot? He plotted weight. Oh, okay, this place. So he plotted all of the values in DISP, okay? So these are all of the values in DISP. So there's a particular value in DISP that is 1.5, and then you can see it's here. It's here. So he plotted all of the values. So we have where is DISP? 0 to 30. Okay. So most of these values are between 200 to, or let's say 100 and something to 600. And then we have one extreme value that is outside, and that is 1.5. So that is what he plotted. For scatter plots, most of the time you actually need two variables for scatter plots. So that's why it plotted this on this side and just put anything for the x-axis. So let's plot DISP against, let's plot it against MPG. Let's plot against MPG. So MPG will be on this axis, okay? So let's plot it against MPG. So empty cars is histogram that takes in one variable. Your scatter plot should take in two. So against MPG. Okay, so you plotted weight against MPG, and you could label your Y as something else if you want, instead of having this. So you can see that you have all your weights here, right? Your weight against this. So most of your weights fall between here and here, and you can see the corresponding MPG values, making and plotting each of the points. So the weight to the corresponding MPG value makes each of the points. But here we have a weight value of 1.5. So this scatter plots to help us to show outliers. So you can see this is standing completely alone here. So this is an outlier. This is a way to recognize outliers. So you could also use scatter plots to recognize outliers. Then you could also do your transformations, your min-max transformations on your data, just the way I explained it, calculating the min-max score and calculating the Z-score using the same formula. You can use it for this particular data. So you can use the empty cars data as your sample data set. And then you could also do the normality and then replot and see if there are changes in the normal plotting, and using the normalized value, you can see if your data is more normalized than before or not. So that is about that. I have to go because I have a meeting for 12 o'clock and I have to go. So if you have any questions, let me know. Please try this out, this remaining out. And if you have any questions next week, please don't hesitate to ask me. But then I will not be able to try this out now because of time. We are way past time and I have to go now. So let me know if you have any questions based on what we've done. And then maybe when you go and come back, if you have any questions in the next class, you can always bring them back. I'm willing to answer. So you can try out the remaining exercises that are in your textbook. And then let me know if you have any issues solving them. But then all of the formulas I've taught us are the formulas that were used in the textbook to create all of these visuals. So you can, if you follow along using the formulas I explained, the normalized formulas and all, you'd be able to understand. So you can take this as an assignment and work on it, and then let me know if you have any challenges working it in the next class. So any questions? Any questions?
No, ma'am.
Okay. All right. Okay, since there are no questions, we'll call it a day. Try the rest out. If you have any challenges working on them, please let me know. Thank you very much. Enjoy the rest of your day.
Okay, ma. Thank you very much, ma'am.
Thank you. Thank you, ma.
Let me see.